Hello, today under classification of polymers, we shall look at crystallinity. So we have seen all these subclassifications, the molecular characteristics also, the various types. And today we shall look at the fifth one, that is the crystallinity, how it affects the polymer properties. So when it comes to crystallinity, polymers may be completely non-crystalline and semi-crystalline, consisting of varying degrees of crystallinity. The crystalline state may exist in polymeric materials. However, because it involves molecules, the atomic arrangements will be more complex for polymers, unlike metals and ceramics. So, in case of polymers, the arrangements tend to be more complex as compared to metals. So, we can think of polymer crystallinity as the packing of molecular chains to produce an ordered atomic array. The chain molecules also extend beyond the unit cell. So we have seen earlier this figure where one single molecular chain passes through various crystalline regions, amorphous regions. So it will pass through various crystallites within the structure. So we come to crystallinity, that is molecular substances having smaller molecules, example water and methane, are normally either totally crystalline or totally amorphous. So if these molecular substances, simple small molecules, if they're totally crystalline, they exist as solids, and if they're totally amorphous, they exist as liquids. So because of the size and complexity of the polymer molecules, polymers are only partially crystalline, or we can call them semi-crystalline. That is, they have both crystalline regions as well as amorphous regions. And one can imagine it in a way where crystalline regions are dispersed within the remaining amorphous material. So any chain disorder or misalignment will result in an amorphous region, a condition that is fairly common because twisting, kinking, and coils of the chains prevent the strict ordering of every segment of every chain. So because of coiling, we have seen earlier that these chains are not able to come together, and so they will form amorphous regions. And so polymers, since they are made up of long molecular chains, it will always be semi-crystalline in nature. So crystallinity means the order or close packing of the molecular chains. Different polymers have different tendencies to crystallize at different rates. So again, it depends on the physical conditions, the chemical nature of the polymer, and the molecular structure, which will decide the amount of crystallinity that is there within a polymer. So all these things will affect crystallinity, and crystallinity in turn will decide certain properties of the polymer. So one can say, since it is the polymers are semi-crystalline in nature, so we can always find out how much crystalline it is. So the degree of crystallinity can be found out. The degree of crystallinity may range from completely amorphous to come to almost entirely, maybe up to 95% crystalline, which is in contrast to metal specimens, which are always entirely crystalline, whereas many ceramics are either totally crystalline or totally non-crystalline in nature. So, when you compare it with metals, one finds that metals which are completely crystalline, whereas polymers may reach up to maybe 95% crystalline by various means. The density of a crystalline polymer will be greater than an amorphous one of the same material. The crystalline, that means, in short, we are trying to say that the crystalline polymer will have a greater density, because the chains are nicely packed, and the molecular weight also, because the chains are more closely packed together for the crystalline structure. The degree of crystallinity by weight may be determined from accurate density measurements according to the formula that is given here. So percentage crystallinity, one can find out that where rho s is the density of the specimen for which the percentage crystallinity is to be determined. So that is rho s, which is found in the numerator as well as denominator, is to be for which the percentage is to be determined is rho s, whereas rho a is the density of a totally same amorphous polymer. If one finds, that would be rho a, and rho c is the density of the perfectly crystalline polymer. So if we were to substitute the values in the above formula over here, the values of Pa and Pc must be measured by other experimental methods. So if we get these values, so one can easily find out percentage crystallinity. So what are the factors then that affect the degree of crystallinity? The degree of crystallinity of a polymer depends on the rate of cooling during solidification as well as on the chain configuration. So during the formation of the polymer or polymerization, the rate of cooling as it is cooling down and solidifying, that as well as the chain configuration will decide the degree of crystallinity. During crystallization, upon cooling, through the melting temperature, the chains which are highly random and entangled in the viscous liquid may assume an ordered configuration. So during the cooling time that is happening, the chains will try to align themselves. The chains that are highly random will try to align and assume an ordered configuration. For this to occur, sufficient time must be allowed for the chains to move and align themselves. So if sufficient time is given during cooling, that is by controlling the rate of cooling, one can modify or play with the degree of crystallinity of the polymer. The molecular chemistry as well as the chain configuration also influences the ability of the polymer to crystalline. So the molecular chemistry, that means what kind of atoms are there or groups are there within the molecular chain, as well as the configuration which we have already seen, that also will decide how much crystallinity can be there in a particular polymer. So factors that affect degree of crystallinity. For linear polymers, crystallinity is easily accomplished because there are fewer restrictions to prevent chain alignment. Any side branches that, if at all found, would interfere with crystallization and are never highly crystalline. In fact, excessive branching may prevent any crystallization whatsoever. Most network and cross-linked polymers are almost totally amorphous because the cross-links prevent the polymer chains from rearranging and aligning into a crystalline structure. A few cross-linked polymers are partially crystalline in nature. With regard to the stereoisomerism, one can say that atactic polymers are very, very difficult to crystallize. However, isotactic and syndiatactic polymers crystallize much more easily because of the regularity of the geometry of the side groups that facilitates the process of fitting together adjacent chains. So, if it is isotactic, it will be more easier to crystallize. Also, bulkier or larger side groups that are there, side bonded groups of atoms, the larger or bulkier the side group, the lesser the tendency for crystallization. So these are certain factors that will affect degree of crystallinity. In addition to that, for copolymers, as a general rule, the more irregular and random the repeat unit arrangements, the greater the tendency for the development of non-crystallinity. So more random the structure, more difficult it is to form a crystalline polymer. For alternating and block copolymers, there is some likelihood of crystallization. Random and graft copolymers are normally amorphous, as one can see the reason why, because graft would be again something like a branch that is coming out of a, the branch of course is of a different monomer, but still the branches are there and definitely they will form a amorphous polymer. To some extent, the physical properties of polymeric materials are influenced by the degree of crystallinity. Crystalline polymers are usually stronger and more resistant to dissolution and also softening by heat. So, higher the crystallinity, the stronger the material, and they would be more difficult or resistant towards heat and dissolving. So, let us see the relation between degree of crystallinity and diffusion. For polymeric materials, our interest is often in the diffusive motion of small foreign molecules, for example, oxygen, water, carbon dioxide, and CH4 groups between the molecular chains. So we would like that these foreign molecules, we would like to see how crystallinity affects the diffusion of these small molecules within the molecular structure or between the molecular chains. So, a polymer's permeability and absorption characteristics relate to the degree to which the foreign substances diffuse into material. So, permeability and absorption characteristics are dependent on this factor, and that is why we would like to see the relation between degree of crystallinity and diffusion. Penetration of these foreign substances can lead to swelling and or chemical reaction with the polymer molecules, and often a degradation of the material's mechanical and physical properties also happen. So that is the reason why we are interested in the diffusion characteristics of any polymer. Rates of diffusion are greater through amorphous regions, as one can imagine. If there are more amorphous regions, rate of diffusion is greater than through crystalline regions. The structure of the amorphous material is, since it is more open in nature. So, foreign molecule size also affects the diffusion rate. Smaller the molecules, faster they diffuse than the larger ones, but natural. So, furthermore, diffusion is more rapid for foreign molecules that are chemically inert than those for the ones which interact with the polymer. So, if they are inert, they are able to go through within the molecular chains more rapidly as compared to the ones which are more of the type which are able to interact with the polymer. For some applications, low permeability rates through polymeric materials are desirable, as with food and beverage packaging. So, in case of food and beverage packaging, we do not wish that the smaller molecules like water that is there present in the food gets through the packaging material and so on. In case of packaging food and beverage packing, low permeability is desirable, as also in automobile tires as well as inner tubes. So, polymer membranes are often used as filters to selectively separate one chemical species from the others. So, that is, for example, desalination of water. So, coming to the next topic of discussion, that is degree of crystallinity and the relation between melting temperature and glass transition temperature. We shall see them one by one. So, melting and glass transition temperatures are important parameters relative to in-service applications of polymers. So, both these temperatures, if we are going to use polymers in our certain applications, we should be aware of these two temperature points and how they work, so that during service we are able to use them more effectively. So they define respectively the upper and the lower temperature limits for numerous applications, especially for semicrystalline polymers. So the range of application would be between these 2 points, that is the glass transition temperature and melting point. So one should be very much aware of these two temperature points, because beyond these temperature points, the polymers might not be so good or effective in their respective applications. So the glass transition temperature may also define the upper use temperature for glassy amorphous materials. So for glassy amorphous materials, one can say that this would be the upper temperature up to which the polymers may be used. So furthermore, TM and TG also influence the fabrication and processing procedures for polymers and polymer matrix composites. So if the polymers are going to be used in say composites, or even if the polymers we are going to process them and form certain articles out of it, so it's beneficial to know these 2 points, so that during fabrication and the processing that is happening to for these polymers, one is able to use them more effectively during these times. So degree of crystallinity and melting point. So let us first see how these two are related. Polymer crystallization is important because the degree of crystallinity influences the mechanical and thermal properties of these materials. The melting of a polymer crystal corresponds to the transformation of a solid material having an ordered structure of aligned molecular chains to a viscous liquid in which the structure is highly random. So, as a polymer starts melting, so what is basically happening within the structure is that the ordered structure that is there of the aligned molecular chains, they transform into a highly random structure. So what happens is there's a transition from a solid material to a liquid because of this transition, because the molecular structure which was more crystalline and ordered has transformed itself into a more random structure. So this phenomenon occurs upon heating, that is at the melting temperature. Melting of polymers takes place over a range of temperatures. Now, again, polymers do not melt like, say, normal other compounds that are there. they melt over a range of temperatures. So whenever you see polymer melting temperatures, it will normally not be one single point. It will be a range between which the melting of the polymer takes place. In any table, if you come across, you'll find there's a range that is given. Also, the melting behavior depends on the history of the specimen, in particular the temperature at which it has been crystallized. So whatever crystallization temperature is there, it will be related somewhere to it. And also the impurities in the polymer and the imperfections in the crystals also decrease the melting temperature. Finally, the apparent melting behavior is a function of the rate of heating. So, rate of heating will also decide how the polymer melts. Increasing this rate results in an elevation of the melting temperature. So, if you want to increase the rate of heating, then in that case, there is a slight elevation in the melting temperature. So, now let us look at the relation between degree of crystallinity and Tg. The glass transition occurs in amorphous or glassy and semi-crystalline polymers. So, semi-crystalline polymers normally do not directly straight away melt like other compounds, say like water, which is in the ice form, and directly at a certain temperature it will just melt, and at a certain temperature during boiling it will evaporate. So there are definite temperature points. But in case of polymers, since it is a semi crystalline material, there is always a range, and there are two specific points, one of them being glass transition temperature and then the melting temperature. It is so it happens due to the reduction in motion of large segments of molecular chains with decreasing temperature. So as the polymer, if we were to cool them, then what happens is the chains that are there, the motion of them, the movement is reduced, and slowly it starts crystallizing. That is when the polymer is cooling. Upon cooling, the glass transition corresponds to the gradual transformation from liquid to a rubbery material. So normally other materials, they directly convert themselves into solid, whereas polymers will first go through a phase where the material transforms itself from a proper liquid to a rubbery material, and then finally to a rigid solid. So the intermediate phase that is there, that the rubbery stage is there, that which is absent in other materials, one will find in case of polymers, and this is where the Tg normally appears. The temperature at which the polymer experiences the transition from rubbery to rigid state is termed as the glass transition temperature, or Tg. Of course, this sequence of events occurs in the reverse order when a rigid glass at a temperature below Tg is heated. So suppose the same thing will happen if a solid is heated, solid polymer is heated, and it will pass through a phase where it goes through a rubbery material, and then it will be converted into a sort of a viscous liquid. So first it will go through glass transition temperature, and then to the melting temperature. So glass transition temperature, there are two important thermal transitions in a semi-crystalline polymer: glass transition and melting temperature that we've just mentioned. Tg is related with the amorphous phase. So first the amorphous phase in the polymer gets affected, and that is where Tg comes into the picture. And on further heating, then the crystalline phase also starts melting, and we get a final melting temperature. So behavior of the polymer at Tg. In the case of a semi-crystalline polymer, the amorphous portions melt or soften at Tg, while the crystalline portions remain solid. An amorphous polymer does not have a sharp melting point. So on progressive heating, the polymer passes from brittle solid to rubber-like solid, which then becomes a highly viscous liquid. So we can look at an example over here. The molecules are glass-like, or rather brittle when we say glass-like, below Tg, and rubber-like above Tg. So natural rubber Tg is minus 73 degrees Celsius. So and there is no melting temperature for this. So minus 73 is the Tg, below which it will behave like a brittle glass-like material, and above Tg, that is above 73 degrees Celsius, it will act like a rubber. So for nylon 6, the Tg is 50. So below 50 degrees, it will be acting like a glass-like rigid material, and beyond 50, it will become rubber-like. and if you keep on go on heating this material further on at 220, it will completely melt. So it must be noticed that elastomeric or rubbery materials have a Tg or softening temperature below room temperature. So in a normal room temperature, the rubber will always exist in its rubber-like form. So it must be noted that the elastomeric or rubbery materials have a Tg or softening temperature below room temperature. As one can see, it is -73, while brittle and rigid materials have a Tg above room temperature. So for nylon 6, for example, the Tg is 50, which is well above the room temperature. And therefore, at room temperature, it will exist like a brittle glassy material. So these are certain glass transition and melting temperatures that are shown over here for various materials in degrees Celsius as well as Fahrenheit. So one can take a look at this table, and these 2 points will be useful during processing. So factors that influence TM: the melting of a polymer takes place over a range of temperatures, thus there will be a range of melting points rather than a single melting temperature. This is because every polymer will be composed of molecules having a variety of molecular weights, as we have seen, and because TM depends on molecular weight. So since each molecular chain will be of different molecular weights, there will not be a single melting temperature for any polymer material. So degree of branching will also affect the melting temperature of a polymer. The introduction of side branches introduces defects into the crystalline material and lowers the melting temperature. The presence of double bond and aromatic groups in the polymer backbone lowers chain flexibility and causes an increase in TM. The size and type of side group influence chain rotational freedom and flexibility. Bulky or large side groups tend to restrict molecular rotation and raise the TM. The presence of polar groups like Cl, OH, and Cn, even though not excessively large, lead to significant intermolecular bonding forces and relatively higher melting points. So, if in any polymer you find these groups that are there, which are polar in nature, then they will tend to increase the melting points. At relatively low molecular weights, increasing chain lengths also raises the TM. The melting of a polymer takes place over a range of temperatures, thus there will be a range of melting points rather than a single melting temperature. I've just mentioned this before. This is because every polymer will be composed of molecules having a variety of molecular weights, and because TM depends on molecular weight. Degree of branching will also affect this melting temperature of a polymer. As we have seen, the introduction of side branches will introduce defects and it lowers the melting temperature. So factors affecting Tg now. Upon heating through the glass transition temperature, the amorphous solid polymer transforms from rigid to rubbery state. Correspondingly, the molecules that are virtually frozen in position below Tg begin to experience rotational and transitional motions above Tg. So whatever molecular configurations the molecular chains have achieved at lower temperatures, as soon as it reaches Tg, they start experiencing rotational and transitional motions above Tg. Thus, the value of the glass transition temperature will depend on the molecular characteristics that affect chain stiffness. Most of these factors and their influences are the same as for the melting temperatures as discussed earlier. So, again, chain flexibility is diminished and Tg is increased by the presence of the following: bulky side groups from the respective Tg values for say polypropylene and polystyrene are -18 and 100. So one can compare that bulky side groups restrict chain movements and therefore rising in the Tg. One can see polypropylene and polystyrene. Polystyrene is having a bulky side group and it will restrict chain movements. Next is the presence of polar groups. For example, Tg values for polyvinyl chloride and polypropylene are 87 and 18 degrees Celsius respectively. So double bonds also affect. So before this, we can just maybe compare these two. presence of polar bond, that is polypropylene does not have any polar bond. So values for polyvinyl chloride, which has got a polar Cl bond, will have a temperature of 87, whereas polypropylene it has got minus 18. So double bonds and aromatic groups in the backbone also affect, which tend to stiffen the polymeric chain. So again, presence of double bond will not allow the molecular chains to move so freely, and therefore the Tg is increased. So increasing the molecular weight also tends to raise the glass transition temperature, just similar to the melting temperatures. A small amount of branching tends to lower Tg. On the other hand, a high density of branching reduces chain mobility and elevates the glass transition temperature. So there is a contrasting phenomenon that may happen, that a high degree or a high density of branches may reduce chain mobility and sometimes may even elevate the glass transition temperature. So a small amount of branching tends to lower, but a high amount of branching at the same time will increase the glass transition temperature due to restriction of chain mobility. Some amorphous polymers are cross-linked, which has been observed to elevate Tg. So cross-links restrict molecular motion. So in short, one can say if molecular motion is restricted in some way, then both Tg as well as Tm will be increased. With a high density of crosslinks, molecular motion is virtually disallowed. Long-range molecular motion is prevented to the degree that these polymers do not experience a glass transition or its accompanying softening. So now let us see Tm and Tg. The same molecular characteristics raise and lower both melting as well as glass transition temperatures. We have seen almost the factors affecting Tg are similar to the factors that affect Tm. Normally, the value of Tg lies somewhere between zero point 0.5 to zero point 0.8 that of Tm in Kelvin. So, consequently, for a homopolymer, it is not possible to independently vary both Tm and Tg. So, if one wants to modify Tm and Tg, it cannot be done in case of homopolymers. It is more difficult to modify them. A greater degree of control over these two parameters is possible by the synthesis and utilization of copolymeric materials. So, in case of copolymeric materials, one can have some control over the Tg and the Tm of any polymer. So, with this, we come to the end of this session on crystallinity. Thank you.